All right. Thank you.
Okay. So good afternoon, everyone. Welcome to our Center for Icons event today. This is Shuai Mo. I'm a co-director for the Center for Icon. So Icon is a center which was launched a year ago with the aim of addressing fundamental challenges in autonomous and client system. Currently, we have more than 60 affiliated faculties, and the center is co-directed by Professor Shreyas Sundram and myself. And one of the key research themes in the Center of Icon is about human-robot teaming. So that's why actually we have our expert at Purdue, Professor Zhang, to organize this series of seminars on human-robot teaming. And today we have a very special guest speaker. He has done very nice work in how to involve human in the autonomy. And actually, I personally know him. He has helped me a lot, and well, and other junior faculty in control field. But I will leave, the introduction of our speaker to our expert and seminar organizer, Zhang. So Nira.
All right, thanks, Shuai. So yeah, I'm very pleased to welcome our friend, Professor Fumin Zhang from Georgia Tech. He is a professor in the School of Electrical and Computer Engineering at Georgia Tech. He received his PhD from University of Maryland at College Park in electrical engineering, and also worked as a postdoc at Princeton. And his research interests include mobile sensor networks, maritime robotics control systems, and more fundamentally, cyber-physical systems. He's the recipient of the NSF Career Award and ONR Young Investigator Program Award. And he's also the co-chair of several excellent journals, including IEEE RAS, co-chair for the IEEE RAS Technical Committee on Marine Robotics, associate editor for IEEE Journal of Oceanic Engineering, and IEEE TAC, and Transactions on Control of Network Systems. So please join me in welcoming Professor Zhang.
Oh, thank you for the nice introduction. So at Georgia Tech, we have a very similar center like Icon called DCL. This morning, we just hosted a wonderful DCL seminar too. So I'm very happy to give a seminar to Icon in the afternoon. So I will talk about things related to human and autonomy integration today. And this work is done by my former students, Paul Warnell, Carol Young, Ning-Shi Yao, and Ning-Shi is assistant professor now at George Mason. Carol is a researcher at Sandia Lab. And also my new student, my PhD student that's about to graduate, Mengxue Ho, and she's looking for postdocs. So if you like the talk, maybe you should consider offer her a position or recruiting her. So what we like to achieve, I think this is common for this field, is to have robots to work with human more efficiently. So over the last 20 years, there's this new movement of cobots where the robots work as partners to humans, right, in different contexts. So a lot of people are actually working on this problem, and our goal is to make the robots behave more naturally, fun to work with, and more importantly, trustworthy, right? So when I started working on this problem, I noticed that pointing motion is a very convenient way for people to interact with robots. And here I'm showing two videos. On the left is a graduate student working with our Georgia Tech miniature autonomous blimps, and he's pointing to different locations where the blimp is going to fly to and land on. On the right-hand side, this is a ETH group where they developed a pointing device so that you can wear it on the hand, and they can use this pointing device to control the movements of the drones. So it's very natural for human to use pointing motion. And actually, because of the convenience of the pointing motion, this motion has been studied by people a long time ago. In 1950, Paul Fitts, a famous American psychologist, proposed a very famous principle for human pointing, which is called the Fitts law. So the Fitts law can be written down with this very simple one-line equation where A and B are some kind of constants. The interesting thing is this I and T. So this t is the time to target, right? If you look at the figure on the right, what the human is trying to do is to move this pointer from a distant d away from the target to hit the target where the target has a size w. So this I here is a log of the ratio between d and w. There are different versions of Fitz's law. They all look very similar. So basically the bottom line is the bigger the target is, right, the easier the pointing task is. And the further away the pointer is from the target, the more difficult the pointing task is. If you move your pointer very fast, right, it becomes very difficult to hit a small target. So this is basically the Fitz's law just says faster pointer movements results in less accuracy. And surprisingly, this principle for pointing motion actually determines a lot of human motion in other contexts. So the recent, if you read Wikipedia, I learned that even the human lip movements or head movements satisfy the Fitz's law. So there must be some kind of general biomechanical principles underlying the Fitz's law, okay? As a control person, so I like to say that actually we can use feedback control to explain the Fitz's law. So basically, you can think of human is actually generating a feedback control law to control the pointer motion, right? Because we want a pointer to hit a target, we're collecting feedbacks, right? So let's just start with the simplest control system that one can have. This is y dot equals the gamma rho minus y. And gamma is a gain, right? Control gain. And rho is the target position where you want the mouse to be, pointer to be. Y is a pointer position that's you're controlling, okay? And most students here, I think, can solve this first order differential equation and from the initial condition where y minus rho equals to d, right? If you don't know how to do it, I'm going to tell you how to do it now. So suppose a target with w can be reached at time t, right? And then you can write down this exponential function as solution for this first order differential equations, plug in w over 2 and d here, and put t here, and you can solve for t, right? Guess what? You get t equals to this nice formula here. And then this is actually Fitz's law, right? You see, you have this 2d over w here, you have this t here. So this very simple one-line feedback control can explain Fitz's law. But wait a minute, is this really what the human's doing? It turns out, it's not exactly what the human's doing. The human is doing something slightly different. So this brings up a more accurate control law that was discovered in 1988 by this paper, a seminal paper here. And they proposed a model called the VIT model, Vector Integration to Endpoint Model, okay? So this is a second order model, okay? And they introduced an internal state called difference vector. This is a hidden mental state of human where it describes where the human thinks the pointer is, right? Rho is still the target position, y is still the pointer position. And then another feature of this model is it actually introduced a proportional relationship between nu and the pointer speed, okay? However, this relationship is nonlinear. And notice that this is 1988, right? At that time, not many people know what the ReLO is, right? Now, because of the deep neural network, everybody knows what ReLO is. So here, they actually use this ReLO function, rectified linear function to scale this nu. The interesting thing is this results a stopping motion of the pointer when you overshoot the target. So let me see whether I can do this well with this target here, right? I'm gonna start my pointer here. I'm gonna move it very fast. You see, I actually overshoot the target and then I stop, okay? So this is what this ReLO do, okay? So they put this ReLO term in here. All right, so why such ReLO term exists? So I will give you some answers later, okay? And needlessly speaking, the most cases where pointer is used is what I'm doing now, moving the pointer on the screen, okay? So, and there are a lot of studies actually carried for human computer interface using a mouse, Okay, so let's see how we can, explain the mouse motion on computer screen by incorporating this kind of feedback control perspective, where you think the human is using a feedback control law, and the pointer is actually moving in certain ways, right? And in this case, the pointer is the plant under control. So we need to have a model for the pointer motion. And as you can, you probably know this, like different operating systems, they move the mouse pointer differently. So one of the things all operating systems do is they actually scale the speed of the pointer depends on the speed of the mouse movement. So your hand is here, you're moving the mouse at certain speed, but then the pointer actually does not move at exactly the same speed as you move your mouse. So this is called mouse acceleration in the literature of human-computer interface. So pretty much the principle is, if you move your mouse very slowly, then the pointer moves slower than your actual mouse movement. If you move your mouse fast, then the pointer actually moves faster. Okay, but then what is exactly the mathematical model for this mouse pointer under control? Actually, this is one of our contributions. This is one of our contributions made by my former student Paul Warnell, and she actually dig into the literature and even the source code of certain operating systems. She actually write down this very simple one-line equation for how the mouse move on the pointer move on the screen. So v dot is actually the actual mouse speed and velocity, or velocity in two-dimensional case. And then this w is how fast the pointer move on the screen. And the key here is this sort of nonlinear gain function, which is a function of the speed of the mouse movement. So for different operating systems, there exists different kinds of the scaling function. Roughly speaking, there are these three types of scaling functions. One is like a constant, like K1, yeah, it's just linearly scaling. And then there's a threshold strategy where they use different segments of gains. So you increase the gains as the speed increases linearly. And then there's a sort of like a continuous scaling up profile. And Windows uses the threshold strategy most of the time. Mac uses this linear strategy most of the time. That's why if you're a Mac user, you switch to Windows, you may not feel very comfortable at the beginning, right? Linux can be super configurable. There are 8 types, different mix of these profiles that you can configure. All right, and this is very interesting. And then let's put these two things together. We have a controller on the left-hand side performed by the human, and we have a plant on the right-hand side, right? And this is a classical teleoperation setup where you can have some kind of delays in this pass, right? So the human is observing this W, right? And at the same time, the human is generating this Y dot, which enters here as a V dot. Okay, so we put these two systems together. We write down the closed loop dynamics on the left-hand side, and guess what? We can prove stability, right? Even given the Rayleigh function, we're able to prove stability of the equilibrium. The interesting thing is the equilibrium is not a single point. The equilibrium corresponding to when the target is either reached or overshoot, okay, because of that Rayleigh reset. But needless to say that the stability result actually help us to understand that the human mouse system is asymptotically stable and robust to time delay as we actually every day experiencing it. So mouse acceleration actually works pretty well for us, and everybody likes it, okay? But what I like to say is that these are all very kind of sort of unsurprising, right, for people in control, right? But what's different as a control person when I look at this thing is not the symptotic behavior. It's actually a finite time behavior of this control law that human is using. So the human actually stops moving the pointer at nu equal to 0. And one interesting fact is when the human actually stops nu equal to 0, the oftentimes the pointers are already overshoot, already past the target. So if you look at the shape of this curve, right, the equilibrium is here. Yeah, this is the equilibrium. This is where the human stops, and this is where the pointer actually hit the target. So the human do something like this, where when the mouse actually hit the target, but then when human actually stop moving the mouse, it's already overshooting. And it also, the human never steer the pointer actually to the equilibrium. Okay, this is very different from a PID controller, let's say, right? And is this really what human is doing? And we wrote this paper here, these two papers about this phenomena, and it get noticed by a very good research team at Beirut University by this Paul Muller's group. And they actually did experiments, collect data on a lot of these mouse pointing motion under different acceleration profiles. So these are, here I'm just showing you like the real human data under two types of acceleration profile. As you can see, these curves, right, demonstrated here, actually matches pretty well with our theoretical predictions. Actually, the theoretical model is not that bad. Of course, there are a lot of details here. Like sometimes the human reach the target by segments of movement instead of just one shot, right? So it moves here, stop here, and move again, right? You can see some of these detailed behaviors. Please refer to their work, look into their papers for more details here. I don't want to go through more details here. You know, we're control people, so we're satisfied with knowing that, okay, the VIT model as a control law, you know, sort of match what the human is doing. So what I like to go next is to ask the following question is, well, we're controlling the mouse pointer on the screen, right? What if we replace the mouse pointer by this blimp? And let's just say we can use our Georgia Tech blimp to really kind of behave like some mouse pointer and try to follow the one movement. Okay. And because our blimp can fly for a very long time, and also they're very safe to human, we're able to do a lot of these kind of experiments, right, on subjects. And we collect the motion of the van, and we collect the motion of the blimp. And the question is, what is the difference between a human blimp interaction and human mouse interaction? Okay. So here, again, we're going to write down the mathematical model. Yeah. So here, the U is actual position of the blimp, and rho is the desired position of the blimp. And as actually Y is the same as before, is the van pointer position. So then we do the same thing, the same mathematical setup of the closed loop system, where left-hand side is the human control law, which is the VIT model. Right-hand side is the one-dimensional blimp motion model, right? The blimp is pretty complicated. It has like 6 degrees of freedom, but in our experiment, we only do this one-dimensional up and down motion. This is why we're able to simplify the mass here. And then the force, you know, exerted on the blimp actually contains two terms. The first one is the aerodynamic drag, and the second one is a feedback control force. So here, notice that we are actually just doing a very simple, you know, proportional control. Okay, on the blimp, just for the blimp to follow the human pointer. Is this the best way of doing things? You know, we can talk about that later. Okay, so. But nevertheless, when you put these two things together, we can actually prove theoretically this system is symptotically stable, and also again, you know, for the human control, the controller stops when mu equals to 0 or overshoot, right? So then we collect the data for several subjects, and we're able to fit their vent movement with a VIT model. The right-hand side shows some of the details of the data fitting. Actually, this line, this jiggling line, is actually the speed profile of the human when they're when the subject is moving the van. As you can see, it's not that smooth, right? There are little jitters in the speed, even though the position changes continuously, but there are little jitters. And sometimes the jitter is due to our localization system, but it's very natural to have this kind of muscle vibration or something like this, right? But nevertheless, we can actually smooth out these jitters and then fit the VIT. This is red lines of fitting the VIT to this this smoothed out curve. Good enough, right? I wouldn't say it's exact fit, right? There must be something that we didn't model with the VIT, but as you can tell, the VIT actually predicts the trends pretty well. And then here's the difference between the interaction between a human and the blimp and the interaction between the human and mouse is we actually from most subjects, right? We actually observe a very more severe a delay in the response of the blimp when the humans switch from moving up to moving down, or from moving down to moving up. And here I'm blowing out some segments of the WAN trajectory and blimp trajectory. Okay, and why is this, right? And also on the other hand, on the right hand side, you can see that the shape of the pointing curve is very different, right, from the shape of the human mouse interaction curve. The human mouse interaction curve was sort of like this, right? But for blimp, it's always tilted to the left, and then move to here, and then this is moving up, and this is moving down, right? So we actually it's a very simple explanation to this is actually the blimp has inertia, right? And also it in the physical world, it has inertia. It has this air drags that it cannot switch its direction suddenly, right? So this brings to the answer to my question on what would be a better control law for the blimp instead of just to follow their the WAN motion, right? I mean, if we consider this factor, maybe there are better control laws that we can design for the blimp to actually follow the WAN or expect the movements of the the WAN and then move ahead a little bit, right? All these things are still open that we're trying to improve the control laws on the blimp. But it sort of give you a general sort of understanding about the difference between human using pointing motion to directed real robot and the human mouse interaction. You have to consider this increased delay. Okay, so then I like to answer the next question is the human's control law is different from PID control law, right? What if we apply a PID control law for the WAN movement to control the blimp? And this is a PID control law obtained by just removing the reload function from the VIT model. Okay, and the blue curve is the performance of PID control law. Every control student can recognize this, right? You got a little bit overshoot, and you get some oscillation. It settles to the desired target. And the red one is actually the VIT control. And you compare this to, you notice that actually the human does not like oscillations. It does not like to. It does not want to. Human does not want to move the WAN back and forth just to get something at the very accurately at that right place. Instead, the human applies something called resetting control, where when things are good enough, I just stop controlling it. And it's a finite time behavior. Actually, in our control community, resetting control have been looked upon before, and it was. I found some papers about 10 years ago, and then it's kind of forgotten, right? So anyway, but it's actually a good idea for human. So now that we understand this kind of increased delayed response when the human is actually interacting with robot, when we move to other kind of human robot interaction context, right? We can actually consider that. One of the important thing to do is to actually have the robot telling the human what the status is in order for the human to have good expectations. Otherwise, you're going to have delayed response. Then the human might misunderstanding the robot. Let's look at a context where our blimp is actually using some deep learning tools to recognize the human face and hand movement. So here, we want the blimp to recognize two gestures. One gesture is the human moving the hand horizontally. Another gesture is the human to move the hand up and down vertically. It's very easy to recognize these two gestures. Okay, a simple machine learning algorithm can just do it. And then what we want to do is to have the blimp to give humans some feedbacks on whether it actually recognized the gestures. So here we have a very simple LED display because the blimp has limited payload. So we use a very small LED display to do the trick. So if it displays this R, that means face detected. And then when human sees this R, the human put the hand near the face. And then the check mark means the hand is detected. And when the human see the hand is detected, start moving. And if the hand detection fails, sometimes the algorithm fails. So and then the blimp displays this message, so the human can kind of restart this process. And then this symbol means gesture is recognized and the blimp is going to react. Okay, so I'm going to show you the real performance of this display system. Like you can see here, the LED is displaying, right? And after it's displaying the symbol, when the human move the hand horizontally, the blimp will just do a spin and then come back and try to find the human again. Okay, as you can see, this display works pretty well, right? And in this experiment, the human is moving up and down, moving the hand up and down. As you can see, after displaying the symbol, the blimp will just move back and flying back and then come back again. Okay, so that's the two experiments we did. And then we collected user data for about, I think 10 subjects in this case, or 12 subjects. So we collect 12 subjects and we divide them into two groups, right? And then we ask them to do this experiment with a blimp with or without the LED feedback. Okay, so and then the two groups, one group do one type of experiment first, and the other group do another type of experiment first, right? And then we collect all the data. And here are the data we collected. So for all groups, definitely when we present the LED display, it takes a shorter time for the human and the blimp interaction to finish. Okay, for the process finish. So on average, with the LED is actually more efficient. And then we ask the human feeling about how do they feel about whether LED is helping. Most of them said yes, okay. But then there are two persons says there's no difference. And then the one person said he doesn't like the LED because the LED scares him. So anyway, but overall, I hope this convinces you that adding some feedback, adding some very simple feedback even from the robot to the human will actually help to smooth out humans' experience, right? So interaction experience. All right. So far, our interaction is actually happening at this sort of, dynamic kind of feedback and motion kind of interaction level, right? One of the new trends recently in this human robot interaction is human-autonomy teaming. So the idea is now like when the robot's intelligence level increases, the robots can actually behave sort of like a human. And there could be behaviors of the robot that generated not under 100% control of the human. Okay, so I'm giving like two contexts. One obvious context is the defense context, and the other one is the medical context, where these group of people in trying to do remote operations assisted by a robot, not in the same room, right? So in these cases, the new trend is, how about we allow the robot to do some decisions that not completely controlled by human, and then how can this robot play certain roles to compensate for the human's roles, right? In this military context, the robot has some very powerful sensors that the robot actually has information that some of the team members don't have. Okay, so can the team members trust robots to make certain decisions? And on the other hand, can the robot learn what the human team member wanted to do, right? Not just by sort of like brute force kind of direct command or typing through the text interface, but sort of just from all the everyday interaction, like based on language, based on gestures, verbal or nonverbal cues, right? So this is actually the recent trend in human autonomy teaching research. So we look into this problem again. We cannot solve this very challenging problem. So we start with something really, really simple, very fundamental. We're just saying that suppose the human, which is a red dot, has several choices. And you can interpret them as goals or roles to play or choices or intentions, whatever. Suppose a human has a probability to select one of these things, okay? And that probability distribution is modeled by this PI, right? And this probability distribution is not known by the robot, okay? And very classical toy problem for this case is if a human and robot meet in a corridor, can the robot predict which side the human will move, right? And suppose the corridor is pretty narrow. Okay, and in this case, there are only two options, and this is the simplest case. And every human has a different probability distribution of choosing either left or right. Okay, and we don't assume the robot has any prior knowledge of the human, and because in human autonomy teaming, there's need for ad hoc teaming. In other words, a new robot just get into the team, right? And then start interacting with people, and later it becomes one of the team members, right? It's just like humans. So that's sort of the goal. All right, and we did some kind of experiments collecting this corridor data. And in this case, our corridor is kind of wide. So we are using, so the actual decision of the human depends on the position of the encountering. Okay, and here we actually we're choosing a very simple learning algorithm called online ensemble learning, which is a baby version of quote unquote reinforcement learning. Everybody's doing reinforcement learning nowadays, right? So anyway, so this is a very primitive algorithm. Okay, so basically it has two experts. So one expert always predict moving left, the other expert always predict moving right. We assign weights for these two kind of expert program. They're not really expert, they're pretty dumb, right? And then we make our prediction by comparing the two weights, okay? If W1 is greater than W2, we choose left. If W1 is less than W2, we choose right. And this is a very famous learning algorithm. And then there are a lot of variation for this learning algorithm. Let's say if a prediction is wrong, then we cut the weights the wrong prediction, the wrong expert's weights by half. If the prediction is correct, then the variation comes in, right? The weights can be kept as constant, or can be doubled or tripled, whatever, okay? So let's just say the robot is using this learning algorithm to learn the human preference. And then I'm listing the two classical online learning algorithm, because the third one is our algorithm. So the first one is if the prediction is correct, the weight doesn't change. The second one is doubling the weight if the prediction is correct. And our algorithm here is a variation of this two classical algorithm, where we say, well, if your prediction is correct, the weight doubles, but then we keep the maximum weight as 0.5. Beyond 0.5, we don't increase the weight anymore. Okay, as you can tell from the reference, like these algorithms are invented many years ago, like 1994 here. Today I'm talking about a lot of the old school results, right? But they're useful. And this one is 1997, right? And our variation comes much later at 2017. For these number of years, when people using these algorithms, one thing they care about is how many errors these algorithms will make, right, in a given number of time. And the interesting thing is actually under different applications, different contexts, the error rate changes. And you see a lot of papers, evaluating this algorithm with error rates and variations of the algorithm, right? And with error rates and all that. And in certain contexts, one is better than the other and all that. So we scratch our head and saying, can we actually look into this algorithm and come up with a different way to characterize their performance, okay? And it turns out that you can actually build a general mathematical model of these kind of online ensemble learning algorithms. All you need is to apply control theory. You you just define 3 state variables, lambda, r, and n, where lambda is the index of the maximum weight. In the case of, I'm only going to talk about the 2 option case, or okay, 2 expert case, but read our paper for the n expert case. We actually solved n expert case also. So for the sake of this talk, I just want to talk about the 2 options case. So lambda is the index of the maximum weight, either 1 or 2. R is the ratio between the 2 weights, the max and the mean weights, right? Depends on which one is bigger. And n is actually the upper bound on the ratio of R, on this ratio R, okay? So you only need these 3 state variables to characterize this big class of online ensemble learning algorithms. Let's start from the most classical one, called the weighted majority algorithm. In this case, the weighted majority algorithm, it can be modeled by the 3 state variables as a Markov chain, which is a random switch. So the P1, P2 here are actually the preference probability for the human that you try to learn, yeah. And the P1, P2 are actually transition probabilities among these 2 states, okay. And the color here indicates the choice. If you're in this gray color, you choose option 1. If in this green color, you choose option 2. Okay, and this is it's surprisingly simple. And then another classical algorithm called Bino, right? And this is the case where the weights will double when if a correct prediction is made. In this case, actually, it's a random walk model where you can have infinite but countably many states. And then, again, the transition probabilities corresponding to the preference. And in our modified model, as you can see, it's actually a sort of a random walk with increasing lengths. Okay, increasing lengths. This is also a Markov chain here. So good. We saw we have mathematical models for all these online ensemble learning algorithms, right? And what can they do, right? How can we leverage this knowledge to characterize performance of these algorithms on this human robot kind of interaction and learning kind of context? Okay, good. We collect some data. So here we simplify this sort of hallway kind of scenario by just letting the robot sit at a place and let humans to pass it from either left or right, and the robot spin and meet the human and collect data. This way, we speed up the data collection process than the hallway content. The hallway, you have to, get the human move around the hallway and all that, and then that's kind of less efficient than this experiment. So we collect some data. In this case, we collect data from 10 subjects, and let me show you some of the data. Okay, so these are data for 5 subjects, where you can see that they have clear preference of either going left or right. So the blue is going left, the red is going right. So you can see like this 1, 3, 7 has a very clear preference, is going right, and 4, 4, and 8 has a very clear preference going left. But notice that even though they have strong preference, they do deviate from their preferred choice from time to time. You see that? Yeah, and no one is just always a left person or always a right person. Okay, yeah. So this is one group of subjects, and in this case, it is curious to ask, how well this kind of temporary deviation from their preferred choice can be tolerated by the online ensemble learning algorithm used by the robot, right? And also we have 2 subjects, subject 2 and 5, actually displays some kind of change in the preference. Like subject 2 originally is a right person and then switched into a left person during the experiment. And subject 5 actually switched not just once, twice. Okay, so then from the online ensemble learning algorithm, we ask the following question: when this kind of preference change, how fast can this algorithm respond to this kind of change of preference and catch up with the new preference, right? Yeah, so that's another perspective of the algorithm. And then we do have 3 subjects that does not have preference. It just, you can see this guy is just left and right, left and right, left and right. And this guy just doing almost the same thing, right? You have this group of humans, right? They don't have a preference, right? In this case, what you wonder is, will our online ensemble learning algorithm even work, right? So then this brings up the next question we're going to ask is, how can we compare these algorithms, right? With all these different kinds of subjects. So we actually inspired again by our control theory, where we have to hit a balance between adaptiveness and robustness. Here we actually introduced two performance metrics. One is called consistency. The other one is called adaptiveness. So for consistency means, the algorithm have to tolerate some temporary concept change. Even though you have a strong preference, but temporarily you deviate from it, can the algorithm tolerate it? Adaptiveness means if you have a permanent, preference change or concept change, how fast, how many steps does the algorithm take, or how many mistakes that the algorithm take to actually catch up with this change? And here we're showing some examples of comparing consistency and adaptiveness. Let's just say on the left-hand side, blue is preferred, and on the right-hand side, red is preferred, and there's a permanent preference change here, right in the middle. Okay, so before the preference change, obviously, if the algorithm keep doing this, right, then the algorithm is inconsistent comparing to if the algorithm is doing this, because there are more switch prediction the algorithm is making. Yeah. So after the permanent concept change, right, now red is preferred, then this algorithm is more adaptive than this algorithm, because this algorithm takes only one mistake to learn the new preference, and this algorithm takes 4. Okay, yeah. So these are concepts that are motivated by the control research before. The question now is, how can we quantify these metrics? How can we find formulas that tell you, how consistent or how adaptive an algorithm is? Well, with the help of the Markov chain models for the ensemble learning algorithm, we're able to come up with those formulas. So here again, remember the gray means the option 1 is predicted, green means option 2 is predicted. So all we need to do now is to have this kind of switching manifold or decision boundary to calculate how easy it is to go from one side to another. So let's just assume that option 1 is the preferred option. Okay, so then adaptiveness actually can be characterized by the mean hitting time to go from the left-hand side to the right-hand side. Okay, so that's a number that can tell you how adaptive your algorithm is. On the other hand, the consistency will be reciprocal. In other words, 1 over the mean hitting time from the green side to the gray side. This means, why is that so? Because previously you were preferring the green options, right? Now you are actually preferring the gray options, right? But temporarily you go back, you go to the green, right? You go to the green. So, but then you don't actually immediately change your let me do it this way. The gray one is you prefer, right? And you temporarily the robot predicts the human prefer. The human temporarily deviated from it, right? But then the robots have to stay in the gray, right? And how many times does it go from the gray to the green? And that's actually that's the time that measures the consistency. Okay, so after we have done this, we can actually write down the formulas for the consistency and adaptiveness of the classical algorithms and also our variation algorithms. So for weighted majority algorithm, right, the adaptiveness is now just P1, just that transition probability, and the consistency is 1 over P2. And then for Vino, the adaptiveness is actually P1 minus P2, and the consistency can be infinity. So if you compare this to algorithm, obviously you can see that the WMA, weighted majority algorithm, actually is more adaptive than Vino. However, the Vino is way more consistent than WMA, right? Yeah. And if you look at our variation here, yeah, you will notice that these two formulas give you numbers just in between these two algorithms. So the MEA actually is a balance between adaptiveness and a consistency. So it's less adaptive than WMA, but more adaptive than Winnow. It's less consistent than the Winnow, but it's more consistent than the WMA. And right-hand side are some large number of simulations. We verify these, but the real convincing result is to apply this algorithm to analyze the data here. These are the data for the 10 subjects. You can see on average, WMA has way more number of switches than the Winnow, right? The Winnow only on average have 1.7 switches. The WMA on average has 6.8 switches across all different subjects. MEA is in the middle, right? And also here I'm coloring these subjects according to their performance. So these red ones are the ones without any preference, okay? And you can see Winnow performs poorly for these subjects without any preference. The Winnow just doesn't change its prediction, right? But WMA and MEA somehow actually is able to catch up with this kind of lack of preference, right? Because the human switch frequently, so the algorithm also switch frequently, okay? And then these blue subjects actually changes their preference when during the middle of this experiment. You can see that definitely the WMA catches these changes pretty well, yeah, and MEA catches this change pretty well for these subject 2 and 5, yeah. But then let's comes to the consistency where we have these 1, 3, 4, 7, 8, right? And these are subjects with clear preference. And with this case, you can see that actually WMA, yeah, if you look at these results, WMA tend to have too much switches. In other words, WMA does not tolerate the temporary deviation from the preference. However, Winnow tolerates extremely well. Okay, if you look at Winnow is like almost 0 switches. In other words, most of the deviation are tolerated, right? But MEA is sort of in the middle. Okay, so it actually agrees with our analysis of the algorithms in terms of consistency and adaptiveness. Of course, so far our consistency and adaptiveness only applies for these simple algorithms. We'd love to generalize this to more complicated algorithms. But before I end today, I want to introduce another sort of exciting new development along this line is, what if we think the human not just a simple probability distribution, but also a learning algorithm running in the human, just like in the case of VIT model, human is running a feedback control law. But in this case, why don't we just think about human is also learning what the robot is doing, okay? And we call this co-learning, okay? So then the question would be, what would be the model the human use? And this is an important concept called zero mind. In this case, we just use again, very old model, 1972 model by Raskoler-Wagner, that on this kind of simple reinforcement learning type of model, where V here is the internal evidence the human is actually accumulating, and lambda is the behavior that the human is observed from the robots. Either in this case, we're doing -1 and 1, either -1 or 1. The human is just integrating this evidence, right? Integrating this its internal state according to the external evidence. And then if VT is greater than or equal to 0, the human makes choice 1. If VT is less than 0, the human makes choice -1. So our idea is, let's put this Raskoler-Wagner model, right, together with the online ensemble model, online ensemble algorithm that the robot is doing, and let's see what can we find from this kind of interaction, right? So we put them together, we notice that actually 2 kinds of steady state behavior can be achieved, even between the interaction between these 2 very simple algorithms. So on the robot side, we're using the DEA, okay, the improved algorithm, like balancing the consistency and adaptiveness, right? On the human side, we use Raskoler-Wagner, And at the steady state, we could have both the human and the robot to agree on either option 1 or option -1. We call these states the agreement states. Okay. However, we also observe there can be a state called, the chatter state, where after a certain time t0, right? So the human and robot always work against each other, and they just keep switching their choices, and they don't agree. So AT always equals -AT -1, and lambda t always equals minus lambda t -1, right? And this holds for t greater than t0. Okay, so and for us in control theory, this is called a limit cycle, right? You could have this equilibriums here as agreements, but also you could have a limit cycle state. Okay, and then the interesting question is, what are the region of attraction for the equilibriums or the limit cycles, right? And when will the learners agree? When will the chatter happen? And using the mathematical tools, we're able to actually write down the formula for it. It all depends on the initial condition of V0, which is the internal evidence of the human. So if the V0 forcing within this range, and gamma here is actually the learning rate, okay? If V0 force within this range, then we're gonna have chatter, okay? Otherwise, we're gonna have agreements. And this is some of the simulation result we show that clearly shows this red region as the chattering region, okay? So in the real life human robot interaction, in this particular case of trying to avoid each other in the corridor, you don't want chatter, right? So then the question would be, how can we avoid chatter by making some changes in the robot learning algorithm? How can we have a ensemble learning algorithm on the robot that can avoid making chatters with human? So it turns out that this is, on the left-hand side, is a Markov chain of the original DEA that we developed, or MEA we developed. It turns out that we can just make very small changes to this algorithm, right? By asking the algorithm to stick to the same choice twice, right? After they selected the new option. Let's just say you encounter a robot in the corridor on the left, there's a collision, and you switch to the right, right? And then you just, and then if the robot also switched to the right, right? Sorry, the human also switched to the right, I'm the robot. And then the robot just say, I'm not going to immediately switch to the left. I am just going to stick to right and just wait a little bit and see what the human will do. Actually, if you think about it, this is exactly how humans resolve this kind of hallway collision, right? So when we encounter somebody, we try to avoid it, and then we just hesitate a little bit, we just wait a little bit, okay? Corresponding to the algorithm is, what we did is we just changed some of the transition in these states. Instead of going to this states here on the left, we actually can just go to a state that after it, and then the problem is solved. So here again, we can theoretically show that even if you start from the initial condition where originally there will be chatter, you can just achieve agreements by making at most 3 mistakes, okay? And then there won't be any chatter, okay? All right, so here are some of the publications that we published over the years on the topics we just presented. I just presented. If you're interested, there are a lot more details in there, including the multi-option learning and some blimp dynamics and all that. Yeah, and also the how did we prove the convergence of the human-mouse interaction under time delay. So if you're interested, feel free to dig this paper out. At the end, I like to thank my sponsors to supporting this research, ONAR and NSF, and also I want to thank the ICON faculty members at Purdue to invite me to give this talk. I really like this opportunity, and thank you for your attention.
Thank you so much. That was really interesting and a lot of really neat examples and old work that you brought out there. Are there questions from the audience?
Yeah, hi, Fumin. This is Zhang. And
hi.
just First, thank you very much for the great seminar. I think it's just a quick question about a few slides ago about you introduced this kind of persistence of robots options. But I think it's kind of similar to the introducing a dwell time for switching control, right? The more like what they've done there is introducing a little bit of delay or dwell time,
right?
To avoid this kind of chattering thing.
Yes, exactly. Yeah. So, yeah. Yes. Introducing dwell time and a little bit extra delays, resolve chatter. That's a conventional wisdom in our community, right? Yeah.
Yes.
So you're right. You're definitely right. But the new thing here is that we are able to actually understand exactly how the mechanism work, right? So let's just say if you don't have the understanding of Markov chain, right? You just say, oh, you just wait a little bit and it will resolve the chatter. Yeah, it will, but why? Right? Yeah. So the key is the why here. The why is the change of this point, this transition from here to here, and that caused the difference.
I see. So in your paper, there must be some theoretical analysis on this, right? To show why. True. Definitely, we'll read the paper. Thank you very much. Thank you. Yeah. Very nice result.
Thank you. Yeah.
I had a follow-up to that. I was thinking the same thing. Did you compute that the 2 is exactly the number of times, like number of options that you want to choose at the same time, or like, I mean, that being sort of a best or optimal dwell time, or does that not fall out from the analysis?
You mean stay the same option twice, right? No,
right.
This is just one way to resolve this contention.
Okay.
I'm not claiming it's optimal. My students don't know how to work that out yet.
Okay.
Yeah. So yeah, that's definitely something we can look into. And also, why choosing this DEA? Why not some other algorithms, right? Maybe some other algorithm does not have a chatter anyway. These are some of the things that we're looking into also. Yeah.
Okay. Other questions from the audience? And feel free to just unmute and start speaking, or type it in the chat if you'd like.
Yeah. Can I stop sharing because I cannot see anybody?
Yes, absolutely. Absolutely.
Okay,
I know it's always tricky with Zoom.
Yeah. Good. Now I can see all of you. Yeah. Yeah.
I had a question while we're waiting, perhaps. Is there any connection to the notion of best response dynamics, right, in game theory? So it's a similar kind of thing where, you're adapting your actions based on what you're seeing the other person's doing, and you'd like to see that it converges to some Nash equilibrium, for example. And then, it seemed very similar to things like repeated prisoner's dilemma, where you have these characterizations of optimal behavior where it's tit for tat and things like that. So I don't know if there's any.
Yeah. I think you're right. So we incorporate the theory of mind model, which is pretty old school stuff, right? But if you want it to be a little bit more modern, you can just think about them as playing a game, right? Introducing a cost function, like one is minimizing, the other one is maximizing, and everybody's it's run for himself, right? And reach a Nash equilibrium, right? So yeah, definitely that can be done. I think I think there might be some brilliant student that can get that done very soon, right? Yeah. The co-learning is very nice. It's very exciting. And the key of co-learning, I think the game theory is definitely a tool you can use to study co-learning. But I think the key is, what is the theory of mind model that you're going to incorporate, right? I mean, that makes a lot of difference. You cannot incorporate just anything. It has to match what humans tend to do, right? So, yeah.
Just to follow up on that, a real quick one, if I have time, just on the first part of the talk where there isn't a robot interacting with you, the mouse model, did you find that humans get better over time at reducing overshoot, or is that sort of a fundamental overshoot that never goes away?
It never goes away. That's the beauty of the Fitts law. It stand the test of time. So yeah. Yeah, and also there are other researchers who did amazing work in pointing, like the Greg Crafton in NRL. So yeah, there are a lot of work in that domain. Yeah.
Thanks.
Yeah, that was particularly fascinating. I mean, I don't actually think about how I move my mouse, but now I probably will pay more attention to how I do that.
Yeah. Secretly, they change the speed you move, right? So that's the thing, and without you even noticing it, right? Yeah.
Maybe one, and I know we're just about the end of the hour. Maybe one quick question that I'll ask. You brought up this theory of mine, and I know a little bit about it, but wasn't familiar with that mathematical model. And I was curious, did you, given how much you've worked with it, do you think that it's actually, even despite its simplicity, sort of pretty accurate, or what aspects of it do you think, where does it seem
okay.
Yeah, what are its details?
Yeah. Theory of mind is actually a pretty new concept in our field. It's a big framework in psychology. It's like optimal control. Like it's a big framework in our community. Optimal control is a big framework, right? So there are many different kinds of theory of mind models. So it's Rascular-Wagner is only one specific thing. And sometimes if you go to that literature, you can get lost there to say, oh, what exactly is theory of mind? It's just a framework, So yeah.
Okay, wonderful. Well, given that we're at 3:01, let's thank our speaker again. That was wonderful. So thank you again.
Thank you.
And I think, I just realized did I send you a Zoom link for the 3 to 4 p.m.